Okay, great, Susana. I think we don't have more question. So thank you very much.
Well, thank you.
We will continue with the talks, which are my
Nice short day.
Thank you. Sandy will be happy.
Okay, let me share my screen. I will give basically, we switch with Suman because I thought he will make a great presentation as he did. And I will just focus in a particular development that we did when I joined LFD, which was related to the measurement of absolute concentration of NADH. But this is also true, not only for the NADH, it's also true for any kind of a fluorophore that we have in the cell and that we can use as a fluorescent biomarker. We need just to do the proper calibration. So the question that I place here is, well, how we can get NADH absolute concentration in vivo by FLIM? Well, in this is a contradiction because from the introduction of then when Enrico presented the phase source and he again emphasized about the independence of the lifetime to the concentration, to the change in the concentration. So how this can work? Well, you know, I will try to address this, basically explaining how we use a light to interfere the fluorescent lifetime or the amount of fluorescent lifetime coming from the NADH with a third component. And I will explain in a second which was this third component and why we pick this. So as I said before, why we would like to do lifetime? Well, it's a very characteristic property of each fluorophore. Many factors can affect the fluorescent lifetime, like ions, pH, hydrophobic properties, oxygen concentration, because it's a good quencher, as Suman addressed before. It also changed by binding, like the case of the NADH. Upon the binding with the enzyme will change the lifetime. And also it changed when you have molecular interactions, such as FRES. So, well, lifetime is a very useful value or technique that we can use for generating contrast and basically do imaging with this. And I place here a couple of examples, one related with the solvatochromic probe Nile red, and these are done with lifetime, and you can see basically all the organization of the ER and also the mitochondria, the nuclear envelope, and the change in intensity means change in the lifetime. And this is a biosensor, it's RAC1 biosensor. And this is done in collaboration with some Amy Edinger in UCI, and we can see the formation of macropinocytosis of these cells along the time with different stimulus. And this is a very nice application that we can find using FLIM. But one of the main thing that for why we always claim for lifetime instead of intensity measurement is because it's independent, and we don't need to think basically that the distribution of the fluorophore that we are studying is homogeneous in the cell. Well, I place a question. Is always independent of the concentration? Well, I will tell you more with this example. Well, NADH is important because it's basically is heterogeneous distributed across the lifespan. So all live cells has NADH. And the good thing is, well, we don't need to dope our sample with any fluorophore. Basically, it is already came with any cell. And basically, it can be split between two populations, the free and bound NADH, depending on the interaction or not with the enzyme. This change in the interaction between free and bound, it changed the lifetime. And these are part of the experiment that Suman showed today. And this was very well described and correlated with the optical redox ratio versus the seahorse analysis for the consumption of oxygen. You might notice that even when lifetime is independent of the concentration, when you have two fluorophore, it's true that you have basically amount of each of both, and this will be affected at the final situation that we have in our sample, because if you have more than one, you will pool the amount of the fraction that you are collecting regardless of the lifetime. The lifetime is still the same, it will not change, but you will have different fractions. So can we stress this in order to use this method to calculate the absolute concentration? And why absolute concentration of NADH is important? Well, basically, as we already know, this trajectory between free and bound NADH, we call metabolic trajectory, and the change toward to free means that we have higher glycolytic condition in our cells. When they move back to the bound NADH, it means that the cells are more close to oxidative phosphorylation, but the concentration is not present here. So how can we measure this absolute concentration? Well, I will try to convince now about how we address this question. So Enrico one day come to me and say, well, Leonel, if we can interfere this system with a third component, and this component need to be something that we can add to the sample, and it's better if we don't need to add something which is that we need to poison. Maybe we can do physically, but in a different way. And he said, well, there is a point in the phasor which is very simple to do. And this point is the one that I am pointing here, 0, 0. 0, 0 means infinite lifetime, so unmodulated light. So he said, well, if you open the room when you are doing the experiment, this will give you a chance. And maybe we can basically interfere our system and quantify after the calibration how much we have of free and bound NADH in our system. So how I started? Well, this was the first lesson that I learned from the LFT. This was really after a few months. And I jumped to the lab trying to be, learn something of building stuff. And I'm very proud of this. I made this gadget, which is basically a flash lamp that I found around. And then I place a diffuser, and then I place a bandpass filter to select different colors. I was trying to use this also for the Laurdan. Then I place an iris so I can measure, I can change the intensity with different step and different size of this iris. And I place ND filters also to reduce the amount of the light. So I place this on top of the microscope, and then I start to do measurement, and nothing works. And I came back to the Enrico's office, and I say, well, Enrico, this is not working, this is not linear, this is not gonna work. And they say, well, can you explain me what you did? So I say, well, I put this, and this, and I say, can you tell me what is wrong? I was trying to explain that I pay a lot of effort to place this diffuser to make basically the most homogeneous that I can, the light and the iris, and say, well, Leonel, this is not gonna work. And it's not gonna work because either changing the 80 or either changing the power of the light, you will change the spectra of the response. And I say, if you want to do it and you have to do it properly, you have to use polarization. So basically, we built just a device that we place in a regular transilluminator. We place two polarizers, and we modulate the light just using the polarizers, as most of the old microscope works, and indeed is the way that I'm using today for the building of my 2-photon microscope. I'm using polarizers, and this enabled us to continue with the project. So what is the idea here? Okay, imagine that we have a solution of free NADH, that we can dissolve NADH in a buffer, and then we can do a measurement. And the measurement will be in this position, which is more or less 0.4 nanosecond. If we shine different amount of light, the position of the phasor will be moved toward 0, 0. Because as much intensity of the light, we will compete basically with the fraction of NADH and our light. So if we do that and we calibrate our system, so how much is this step, how much is this step, how much is this step, and then we place everything in our software, we can determine where is the shift and how we can calculate the absolute concentration of our system. Okay. Well, I was very happy because everything was working, and Enrico come back the next day and say, well, Leonel, I found another way. You don't need to use your polarizing. I say, no, come on, Enrico, I spent a lot of time. I think this is a very nice construction. I am very proud of this. Say, well, look at this, Leonel. Well, if you think about, we can add electronically as much light as you want because it's an infinite component. We can place in our system a third component with an infinite lifetime. And we did it, and we did the calibration from the measurement and the electronical light, and basically everything came in a line, which is very nice because now we don't even need to do this calibration with different amount of the light and the concentration. We just need to take one record of the absolute concentration of NADH before or after we measure our cells. Okay, how this work? Well, we have our sample, we place our lamp, and this moves toward a certain distance, and we label this distance with the concentration that we know, and then we do the same electronical, basically the software does this for the bound. And we need to take care of something because the quantum yield of the bound NADH and the free NADH is different. It's more or less 7 times different. And you may notice that the distance for the same amount of light that moves the position of free NADH towards 0, 0 is that long. However, for the bound is this little long. And this is due to the quantum yield. It's more hard to move the bound NADH toward to 0, 0 than the free NADH. But we can calibrate this and the software does all the work. So then we have a measurement. This measurement were done by Nick Ma, a PhD student of Michel Digmar lab. And basically here we have the classical free and bound trajectory. And if we place a cursor, we can see that the short lifetime is inside the nucleus, which is something that we already know because there are no metabolic enzyme there. And then we have the long lifetime in the rest of the cytoplasm. And this is something that more or less we, at that point when we were doing the experiment, was known. And then we apply our lamp. And as soon as we apply our lamp, we notice that the concentration were different along the cell and more complicated than the situation that we have here. So first of all, we can see that there is a spread in the data, very long, and then there are some very bright spots here. So this very bright spot here, which are this red selection here, is basically a concentration of NADH, which is very homogeneous in all this region because it's very concentrated here. However, in the line, we have really a variance of concentration of NADH, regardless of the free and bound. We can also tell which is the fraction of the free and bound. So we can do first the fraction of free and bound, and then the absolute concentration of the fraction of free and bound. So you may notice that the most strong area, which is this one in red, are associated more or less where we expect to have the mitochondria, where the bound NADH will be more important. And the less one concentrated is here in the blue cursor, which is in the perimeter. And we know that there are some enzymes we use that use NADH and also NADPH because we cannot discriminate between NADH and NADPH in this experiment. So then we did this, we analyze, we make a scale to color the range for the concentration. And basically, after all, the story ends basically measuring the concentration of NADH in the whole cell with the pixel resolution on an in vivo cell. We did all the calibration and we were very, very happy because the concentration that we got is more or less what was described by biochemistry experiment. And this is very interesting because if you think about to do any kind of measurement of absolute concentration, traditional biochemistry need to distort the sample. You need to break the sample and do experiment in analytical fashion. In that case, we can calculate the absolute concentration of a fluorophore without even affecting our system. It's just by a calibration that we did before or after our experiment. And the only considering that we need to have is that we need to keep our system in the same condition, meaning same laser power, same calibration for the detector, etc. So this is conceptually what I would like to tell in this presentation. I want to thank, of course, Enrico for giving me the chance to work in this, and also to Michelle Dickman, because this was a project of Ning Ma, a PhD student of Michelle, as I said before, and I enjoy a lot working together in this project. And we have the paper, and there are some other people working on this using the absolute concentration. I found very nice, interesting to add to the traditional free and bound NADH also the absolute concentration analysis. Here is Michelle and Ning and all the LFD troops.